Welcome to Brain Vision.
So the torque on the rotor will cause an angular acceleration. This is given by alpha equaling the torque on the rotor divided by the moment of inertia. We know that the torque and the angular acceleration will have the opposite sign of the initial angular velocity because the rotor is being brought to rest. We're going to use the rotational inertia of a cylinder. Therefore, we're going to use I of a cylinder. We can say that, or rather, we can say that this is going to be equal to torque divided by the moment of inertia of a cylinder. And then we can say that we can use this equation, omega final squared equaling omega initial squared plus 2 times alpha times the change in angular displacement, and then solve for the angular displacement. So the angular displacement would then be equal to omega final squared minus omega initial squared divided by 2 times alpha. This would be equal to, the rotor is being brought to a rest, so we can eliminate this term. This would be equal to negative omega initial squared divided by 2 times the torque divided by the moment of inertia of a cylinder. And we can then say this is going to be equal to negative omega initial squared divided by 2 times the torque divided by 1/2 mr squared. That would be the formula for the moment of inertia of a cylinder. And then we're going to simplify. Delta theta would be equal to negative mr squared omega initial squared divided by 4 times the torque. And at this point, we can simply solve. So delta theta would then be equal to negative 3.80 kilograms multiplied by 0.0710 meters squared multiplied by 10,300 RPMs multiplied by 2 pi radians for every 1 revolution multiplied by 1 minute for every 60 seconds. We're going to square this entire term. And then we're going to divide it by 4 times the torque. So 4 times negative 1.20 Newton meters. We find that delta theta is going to equal 4,643 radians. Let's convert to revolutions. So 1 revolution for every 2 pi radians. And this is giving us approximately 739 revolutions. So this would be our total angular displacement as the rotor is being brought to a stop. For the time, we can say that the change in angular displacement would be equal to the average angular velocity, so 1/2 times omega initial plus omega final multiplied by the time. Therefore, the time would then be equal to 2 times delta theta divided by omega initial plus omega final. We know that omega initial is going to be 0, so this term can be eliminated. And let's solve. So 2 times 739 revolutions divided by 10,300 revolutions per minute. And then we're going to multiply this by 60 seconds for every 1 minute. And we obtain a time equaling to approximately 8.61 seconds. So this would be the time taken for the rotor to come to a stop. That is the end of the solution. Thank you for watching.